In this session, we're going to talk through some of the factors that affect why some acids are stronger than others. And so it turns out it all depends on the strength of the HA bond, where remember A is the conjugate base, sort of the rest of the acid. So it all depends on the strength of that bond. And there are really two things that we'll talk about that can affect that bond. One is electronegativity differences, so that if there's a bigger difference in electronegativity, that's going to make for a weaker bond. And also, we're going to talk about orbital overlap and thinking about size effects. And so we see that those electronegativity differences and size effects are both part of the equation, but one of them is going to dominate. And which one dominates depends on which trend we're looking at. So take, for example, this series of CH4, NH3, H2O, HF. So we're going across the periodic table. If we look at acid strength, we see that HF is the strongest acid in this series and CH4 is the weakest acid, and that this tracks with the electronegativity difference between C and H, N and H, O and H, and H and F. So that when we have the biggest electronegativity difference, because F is the most electronegative, then we have a stronger acid. And so let's think about that. The very electronegative F is hoarding all of the electrons, is polarizing that HF bond, so that there's relatively little electron density on H. Because there's less electron density between the two atoms, that makes the bond between them weaker, and therefore the H is more likely to dissociate, and that means a weaker acid. We see that here bond length doesn't really play a role. So if we look at the differences between the CH and the FH bonds, we see that they're about the same. So here they're all about 1 angstrom. And angstrom is 10 to the minus 10th meters. It's just a common unit for length. If we look instead at the series going down the periodic table, HF, HCl, HBr, HI. HI is the strongest acid. HBr and HCl are also strong acids in water, meaning they dissociate completely. HF, on the other hand, is a weak acid, so it's the weakest in this series. If we look at the electronegativity differences, we see that HF actually has the greatest electronegativity. So if electronegativity were the dominating factor here, we would expect HF to be the strongest and HI to be the weakest, but that's not what we see. Instead, the bond length or size effects matter here. So HF has the shortest bond, so the H and the F are closest together, and HI has the largest bond, and now we go from 1 angstrom to 1.7 angstroms. That's a much bigger difference. And so we can kind of think about this in terms of orbitals. So if you think about HF, we imagine the HF bond made between the hydrogen 1s orbital and a p orbital on F. And maybe they look something kind of like that. And so if we imagine the same thing happening with the HF, maybe we have something like our hydrogen at 1s orbital here, but then the I orbital. So I is much further down in the periodic table. This is going to be a 5p orbital. That is going to be a whole lot bigger. Oh, wow, it doesn't even fit on this slide. It's so much bigger. That I orbital is huge. And so that means that the I and the H are not getting very close together. They can't make a strong bond because their orbitals are mismatched in size. So as a result, the HI bond is much weaker, and therefore HI is a much stronger acid compared to HF. Okay, so here's a different trend. When we have these oxyacids, as we sometimes call them, look here, we've got HOI, and we're comparing with HOBr and HOCl. Now the bond we're interested in is always the same. It's an OH bond, but we're changing some Y group that is attached to the O. So here, size effects don't matter because the overlap of orbitals is always between H and O. But we can look at how that Y addition is going to change the OH bond. So here, Cl is the most electronegative, and I is the least electronegative, and we say that HOCl is the strongest and HOI is the weakest. And the way we can think about that is that if we have a really electronegative Y group, it is going to polarize the OY bond, drawing electron density toward itself. Oxygen's pretty electronegative too, so it's going to compensate by polarizing the OH bond, drawing electron density toward oxygen. That's going to weaken the OH bond and make for a stronger acid. So the OH bond in HOCl is weaker than the OH bond in HOI. And so that's going to lead to a stronger acid, HOCl, and a weaker acid, HOI. Okay, so now we've got oxyacids. We're keeping that OH bond constant. We're even keeping the Y constant. But now we're changing the number of oxygens that are on Y. So we're going to have, some number of oxygens, which really is the same as changing the formal oxidation state, or the sort of formal charge on the Y atom, which here is chlorine. So as you can see, as we add more oxygens, we also get stronger acids. So as we add more oxygens, we get stronger acids. And the logic here is pretty similar to what we saw in the last slide, where when we have HOCl, Cl is drawing electron density toward itself, and oxygen responds by drawing electron density away from hydrogen, which weakens the bond. Now, when we start adding more oxygens, those oxygens are pulling electron density away from chlorine, which then pulls electron density away from that oxygen, which polarizes the OH bond, leading to a much stronger acid because a much weaker OH bond. Okay, so let's put these together. Which of these three is the strongest acid? So we said before that to make a stronger acid, we want to increase the number of oxygens and we want to increase the electronegativity of Y. So for the electronegativity of Y, chlorine is going to be bigger, more electronegative than bromine. And that 3 oxygens is obviously greater than 2. So the strongest acid is going to be the one that has the most oxygens and the most electronegative atom, and so that's going to be